Hello, Chem 2. Welcome to the last video that's associated with equilibrium and the concepts therein for Chapter 12. What we're going to do today is we're going to introduce a concept called LeChatellier's principle. That's how I pronounce it. If you watch the videos that I've shared with on OneNote, they pronounce that his name many different ways. I just say LeChatelier. This is the way I pronounce it, but there's many ways. But the concept is to talk about what happens when conditions of a system are changed or altered, or the word that we're going to use, the word of the day, is stress. Now, I'm going to start by saying this is a difficult topic for me because this is one of my favorite lectures to give in person. There's so much fun associated with this lesson. It is one that I created many moons ago as a way to clearly describe with my weird analogies and some demonstrations, but of course that's not possible here. So I'm going to try to go back and forth between a couple different topics and try to do the best with this, but a little sadness on my side, sitting in a room in my house in Sykesville trying to describe LeChatellier's principle. I find it to be a little difficult. I love this topic. It's probably my favorite. Again, it's probably one of my favorite lectures of the class in general. So I'll do the best I can with it, with the descriptions I have here. So let's start with administrative items. You have the optional out, you have the required out, and then the Unit 12 test should be popping up. If not today, Monday, tomorrow, Tuesday. And again, you need to get a 75% on the required out in order to be able to take the Chapter 12 exam. Please come with your questions in the required outs during the Teams meetings. We will be meeting this week on Wednesday and Thursday, again from 2 to 3. Come with questions. I love when you guys come with questions. It's less of me just saying, here, do the problem. I love when you guys have tons of questions so that I can quickly help you guys to the best of my ability in that time frame. So let's get to it. So this is Chapter 12, Gaseous Equilibrium. We're going to do the last thing, effect of changes in condition on a equilibrium system. Okay, so we're going to talk about stress. We're going to talk about stress and the stress that might be placed upon anything. So let's think about it. If you were personally, like for instance, you had to stay home and you had to make the best of a situation where you were cooped up and you couldn't see your friends, what would you do? Well, you would try to find a way, hopefully, and you have done this for the last 2 months plus, you would find a way that you could relieve that stress. You could minimize that stress. You could minimize the impact of that stress. So let's use the fact that you haven't had a chance to see your friends in a very long time. Well, you might find yourself texting them more often. You might actually, heaven forbid, use the telephone as a phone and call them, or you might FaceTime them, or you might Zoom with them. And I've seen even students who will go to the school parking lots in their individual cars from a distance, practicing your social distancing of 6 feet or more, and chat with their friends because they want to relieve that stress that's associated with the stress that's placed upon them. Well, chemicals are not any different. Chemicals are not any different. If you were to take a system that is in a non-stressed situation, that's what equilibrium is all about, and you were to stress it, it is going to react, change, redirect itself in such a way that it is going to try to reduce that stress. And that concept is called LeChatellier's principle. LeChatellier's principle says when a system is in equilibrium in that nice cozy time and is subjected to a stress, it is going to shift in a direction. Shift towards the product, shift towards the reactants, but it's going to shift in a direction that tends to relieve that stress. Let me explain to you what that means, show you an example of what that means. Now, we're going to address in this video 3 different types of stress. Stress number 1 is going to be probably the most common, changes in concentration. Hopefully you'll see what I mean by that, where we'll change the concentration of one or more of the reactants or the products, and the system is going to go, whoa, Nelly, what happened? That's crazy. Let me get back to equilibrium. You just mucked me up. I'm going to change temperature. I've already said that the only way that you can change a rate law constant and or an equilibrium constant is by changing the temperature. Well, how does that work? How does that changing the temperature affect the position of the equilibrium? And then the last one is very, very specific. It only works with gaseous equilibrium, and more specifically, gaseous equilibrium when you have a disproportionate or unequal number of gas molecules on the two sides of the balanced chemical equation. There, if you change the volume by compressing it or expanding it, then the pressure is going to change inside, and the system is going to adjust to try to change the pressure. So let's do these one at a time. First one, concentrations, changing concentrations. Now, the reason why I kind of like this particular lesson is I use a series of analogies and demonstrations, and all I ever can really do today is talk in terms of concentration. I've linked within this PowerPoint a demonstration that kind of shows all the stuff that goes on. It's a very old demonstration, an old video one. And I'm going to leave it up to you to go ahead and watch that so I don't get hit with any copyright infringements. But when I post this PowerPoint, on a lot of the tops, it'll say Cobalt reaction. I'll show you where it is. If you click onto that, you're going to be able to watch a video, a really brief video, seeing this reaction in process, the one that I would have used in class. But let's do the analogy. Okay, so here's my analogy. I'm going to argue, and this is where it gets kind of awkward and uncomfortable. I'm going to argue that coupleization, that's the word I use for it, coupleization is an equilibrium reaction. And what do I mean by that? Well, girl plus boy makes a couple. And then we're going to deal with the more typical, not judging at all, I'm just using this as an example to make life a little bit easier. A boy plus girl creates a couple. But here's what also happens. I know this because I've been working in high school for 22 years now. Couples break up. Couples are made, couples break up. Couples are made, couples break up. Couples are made, couples break up. And this is a dynamic equilibrium where it's constantly boy finds girl, make a couple, boy and girl love each other for a long, long time, and then they had enough of one another and they break up, and the mix all starts up over again. Maybe with the same exact partner, maybe with different partners, but the reality is this is an equilibrium. So let's talk about stress. Now, the story that I always tell, and again, it is totally fictitious, but it just kind of makes my point, is to suppose there was within Carroll County this private school down the road. It's over there. I don't know where it's at, but it's over there. And the private school, it has a healthy population. It's an all-boys school. It is a private school. It is all boys, private, and their chemistry teacher is not nearly as proficient as yours. And they do a lab one day, and something happens, and a section of the building blows up. Boom. And suddenly there's this large population of boys that need or would like to continue to get an education. And Mr. Booz, our principal, goes along and says, you know what? Century has the space for you. So let's try this. Guys, come on down. Come on, we'll put you into our classes. We'll go ahead and make you be a part of our Century Nights, and we'll continue with your education. So what do? We take the system that is at equilibrium, is flowing very smoothly, and we add a stress. The stress we're going to add is add a whole bunch of single boys. Single, you don't know them. They don't know you. They popped into the situation, and suddenly we have an influx, an additional number of single boys coming into the building. What's going to happen? Well, I don't know because I'm not a high school student, but I've watched it long enough. But if we were to suddenly add, say, 200-300 single boys into our system, my guess is that what would happen is we would suddenly have this shift of the equilibrium. We would have it where suddenly we would have more coupleization because the girls would have more to choose from. Instead of having just the typical Century boys, no disrespect, guys, but I'm going there. No disrespect, we suddenly have an influx of non-Century boys. And more girls might find more of those boys more appealing, and we would have an increase in couples. So we would increase the number of couples, and we would decrease the number of single girls. Because you notice we didn't add any more single girls. We just added more single boys. Well, that's a stress. That's a stress on the system. And notice what happened here. The system responded to the stress. I add something to my reaction. I add something to my equilibrium. It is going to shift in such a way to try to shift towards or away from whatever I added. Now, while I have this on the screen, I'm going to at least address one other way that I usually share this as a stress thing. My brother is still a special individual, but when growing up, my brother had a propensity for bringing stuff home, junk that the neighbors left out or the neighbors didn't want anymore, and suddenly all this stuff, these tractor parts and lawnmower parts and bicycles and all these mechanical things would show up in our yard. Well, that was a stress to my dad. My dad would say, quote unquote, get that stuff the heck out of my yard, with a lot more expletives in there than I just expressed. Stress adds stuff to the system. My backyard had more junk in it. Response, get the stuff out of the yard. When you add something to an equilibrium, the system is always going to respond in such a way to try to relieve or to remove. If I add to the left-hand side, it's going to shift to the right-hand side. If I add to the right-hand side, it's going to shift to the left-hand side. So example number 2. Suppose I also have the possibility of removing couples. Now here's my thing. I'm going to argue that a couple, a attached couple, is not the most productive member of education society. That's my way of saying they kind of get too wrapped up in the lovey-dovey of one another, and they're just not as good as students as they can be. Now, I'm just using this as fictitious. I'm not saying that's my true feeling, but I'm just going to use that as an example. So suppose when that school got rebuilt down the road, Mr. Booz has a really good idea with the help of Mr. Ferrin, and we say, you know what? We want to make sure that we have the most studious members in our building. So let's take all those distracted individuals and let's shuffle them off to the new school when it's built. And yay. So what we're going to do is, as a couple is formed, you can't come back. We're going to ship you off to another school, and we're going to remove couples. Well, what's going to happen here? What's going to happen here? Well, let's think about it. If I were to remove couples, then what we're going to have in the building is a bunch of single boys and single girls. And not to be too graphic, but single boys and single girls will do what single boys and single girls do. They're going to find somebody in the works that is appealing enough, and they're going to respond by coupleizing, and you're going to make more couples. And then we're going to ship them off, and they're going to have single boys and single girls, and you're going to find somebody who's appealing enough, and they're going to make more couples. So what's going to happen is both the single boys and single girls are going to decrease as you remove the couples. So we remove the couples from the situation. It's going to make more couples. Remove, make more. Remove, make more. Remove, make more. It's the opposite of our previous analogy. If we add to a system, the system is going to respond in such a way that it tries to get rid of whatever you've added. The opposite, if you remove something from the system, it's going to shift in such a way to try to remake that thing you're removing from the system, because it wants to get back to equilibrium. So we have this response that's going to take place. So if I had this reaction, this equilibrium, and I were to add BR2, so I'm going to add the BR2. Well, if I add the BR2, it's going to shift in such a way that it's going to try to get rid of the BR2. So it's going to try to remove the BR2. The way that this system responds to get rid of the BR2, the bromine gas, is it's going to shift towards the left, which means I'm going to make more of the BRNO, and I'm going to make less of the NO while trying to remove the BR2 from the reaction. It's going to shift to the left. If I add BRNO, if I add the bromine nitrogen oxide compound, I were to add that, then what it's going to do is it's going to shift away from that again. It's going to shift in a way to try to remove the BRNO, and it's going to shift towards the right. It's always going to shift. If you add something to a system, it's always going to shift in a way that's going to try to get rid of that. So it's going to shift away from it. That means in this situation, NO will go up, Br will go up, and ultimately BrNO will go down to try to minimize the stress. What if I remove the NO? What if I take this out as it's being made? Well, it's going to try to make more. The way that this system makes more of the NO is to shift towards the right. So Br is going to go up. NO is going to go up also, trying to remake the NO that has been removed. And as a result, BrNO is going to decrease. So shifting and concentrations are going to happen based on the direction or whatever you add to the system. If you add something, it's going to shift away from it. If you remove something, it's going to shift towards it. Now, this is the Cobalt Equilibrium that I said, and you can see that the header here is underlined, and to avoid copyright infringements, if you hover over this, this has under here a video that shows this chemical reaction in action. I'm just going to use it as my descriptor here. What you're going to see if you watch the video is a mixture of cobalt hydrate, which is the compound on the left, which is written in red, and cobalt chloride, which is on the right. And you're going to have this mixture that's going to be somewhere in the middle between red and blue, which is like purplish pink. So in this situation, if I add HCl, which provides my Cl molecules, it's going to shift towards the right. And it's going to make more blue and make less red. And these two ions have those colors. So when I add chlorine, add hydrochloric acid, it's going to actually create a bluer environment. If I add water, it's going to shift away from the water, and it's going to come back over here, and it's going to become pink. And again, if you watch this video, you're going to see this equilibrium take place, and this is a demonstration I would normally do in class to show this system responding from one side to the other and going from red to blue to red. And then finally, the last thing I would do in class, I would add silver nitrate. Now, silver nitrate is a compound that will react with the chloride ions and will remove the chloride ions. So if I'm going to remove the chloride ions, I'm going to try to make more chloride ions, and it would shift to the left and become pink again. Again, watch the video, and you'll see that again. I don't want to get into any copyright infringement issues with that video, but it's a very, very good stepping stone where they're going to do exactly those 3 steps, plus some of the steps in the subsequent parts. So if you want to pause this video and watch that, you can go ahead and do that. And then I'll come back. You can come back to this and we'll talk about temperature. Okay, so what about temperature? So let's talk about temperature from the state of the analogy we dealt with before. Boy plus girl equals couple, and I'm not going to be stupid. I'm going to say that heat is probably going to be a byproduct. Boy plus girl equals couple and some heat. So this is an exothermic process. Boy plus girl gives you couple plus heat. Well, effects of change in temperature is going to be essentially treating this reaction in a way that heat is in this situation, a product. If this was an endothermic reaction, then heat would be a reactant. And you essentially are going to treat heat as being a reactant or a product. And when you increase the pressure, you're adding heat. So it's going to shift away from the heat. And when you decrease the temperature, you're going to be removing the heat, which means you want to make more heat. And you're going to treat it the exact same way you did the previous example with determining the direction which is going to shift. Now, here's the difference. We're not adding or removing any reactants or products. So in this situation, our K value, our KEQ, our KP, our KC, whatever it's going to change. Our KEQ value is going to change. If the system shifts towards the right, the K value is going to increase. If it shifts towards the left, the K value is going to decrease. Remember, it's products over reactants. If you make more products and make less reactants, shifting towards the right, that is going to increase your K value. So is this changing in temperature is the only way, changing in temperature is the only way that you are going to be able to change the K value, the KEQ value of an equilibrium. Let's see how this works. So I always use the analogy to say, well, let's play with this thing. And we know that boy plus girl equals couple, gives heat. So we're going to make make this into a real life example. So I'm going to say every time that you find that love of your life, you go up to Miss Lawless in the front office and you say, Miss Lawless, I love this guy. He's amazing. He's spectacular. And Miss Lawless has to bump up the temperature of Century High School 2 degrees. Bing, bing. However, since the reverse reaction is going to be losing heat, every time a couple breaks up, they go up to Miss Lawless in the front office and say, Miss Lawless, I'm done with this guy. We're done. And she turns down the temperature of the high school 2 degrees. And she goes to the thermostat up, down, up, down, up, down, as many times as she needs to as she gets these announcements of making up and breaking up. So I'll ask the magic question. What's going to happen to the temperature of Century High School throughout the day? Well, it's in equilibrium, which means the rate of the forward and the rate of the reverse are going to be equal. So I argue that all we've done is drove Miss Lawless crazy by having her play with the thermostat all day long, but the temperature of the school will not change because the rate of the forward is equal to the rate of the reverse. The number of times she dinks up the temperature is going to be equal to the number of times she dinks down the temperature until we provide a stress. Suppose I say, Miss Lawless, let's have some fun here. Let's stress the system out. Let me just go ahead and bump up the temperature of the building a solid 15 degrees. Let's see what happens. Well, I'm going to argue, again, from an analogy standpoint, that some of those relationships that are on the fringe, like you're putting up with the person as much as you can, and you want to consider staying together as long as you can, but it's hot. So if I get to dump you, I can go up to Miss Lawless and say, Miss Lawless, we're done. Can you please turn down the temperature 2 degrees? So what I'm going to say happens if I increase the temperature, the system is going to respond by having more people break up. We're going to get more single girls, more single boys, and a decrease in number of couples. So we're going to have a decrease in our K value, and we're going to have a complete alteration of the position of our equilibrium. It's going to shift to the left. And Miss Lawless says, that was mean. Why'd you go and do that? That was not cool at all. Why would you do that? And I say, well, let's see whether it works the other way around. Let's decrease the temperature. Let's make this place cold as all get out. Miss Lawless, let's have some fun. Let's drop the temperature of the building to a solid 20 degrees below what is normal. So it's normally supposed to be 65, 68 in here. Let's drop it down into the 40s. Let's see what happens. Well, I would argue, again, from an analogous standpoint, that maybe you can put up with that person for a little bit. If you're willing to say, you know what, let's go to Miss Lawless and let's go tell Miss Lawless that we're together. I'll be your boyfriend, you be my girlfriend, and we'll go ahead and we'll get Miss Lawless to turn the temperature up 2 degrees. So the system is going to respond by making more couples and less single boys and single girls. The K value increases and we adjust the position equilibrium because we've stressed it out. Notice what we've done. We've just treated heat as a reactant or a product. If you add a component, it's going to shift away from whatever species or whatever component you've added. If you remove a component, in this situation heat, it's going to shift in a direction to try to increase that material. In this case, since we decrease the temperature and the temperature is on the right, it's going to shift towards the right. So one of the classic equilibrium reactions, and again, I included on your OneNote page some stuff about the Haber process, or the Fritz-Haber's process of taking nitrogen and hydrogen and making ammonia. It is actually, in some arguments, and I was looking through this, can be argued by quite a few chemists and scientists that it's in the top 10 most important reactions in history, where they took the nitrogens in the air and added hydrogen to it and made ammonia. Well, this reaction is an exothermic process. It's an exothermic process. So if I increase the temperature, it's going to shift back to the left. And that's a bad thing. So our logic would say, if I want to make this reaction go more towards the right, I want to decrease the temperature to make it shift towards the right. However, what did we learn in the last chapter about decreasing of temperature? What happens to the rate of the reaction when we decrease the temperature? It slows down, doesn't it? So the position of the equilibrium, once it gets to equilibrium, would be more towards the right, making more of the ammonia. but it would take longer to get there. So this is a catch-22 in regard to the Haber process. The Haber process does make the ammonia, but it has to be at a reasonably neutral temperature, so that it doesn't react so slowly that getting to the right-hand side and making a decent amount of the ammonia just takes forever, but not so hot that it keeps the system from being too much to the left, so not very little of the reactions and products take place. So it's a catch-22, but anyway, that just affects the temperature. If it's endothermic, meaning heat is on the reactant side, then if I increase the temperature, it's going to go away from the heat, so it's going to shift towards the right. And if I decrease the temperature, it's going to shift towards the heat, which means it's going to shift towards the left. So big picture, both concentration and temperature. If I add something, it shifts away from whatever I added. If I remove something, it shifts towards whatever I remove for both temperature and for concentration. And again, with the Cobalt Equilibrium, if you watch this, you get a chance to see, and I'll give you the side note, that this reaction, when I put it in hot water, it's going to become blue. And when I put it in cold water, it becomes red. So is this reaction exothermic or endothermic? Let's think about it. If I put it in hot water, it's going to shift towards the right. So that would mean that heat is on the left, which means this is an endothermic process. So this reaction is endothermic. Okay, last one, changes in pressure. Now, pressure is difficult. And actually, again, there's a video link here that tries to show an example of a pressure change. Pressure is harder to see, and pressure is harder to observe the differences because of the fact that you're talking about very often pressure only works on gases, and you have to have gases that have different colors. In this chapter, it started off by talking about a reaction of N2O4 and NO2 and its equilibrium where it went from a brown to a colorless. So that was a good example of one where you could see the color, and actually that's the example I think they use in this video. But let's talk about what happens to pressure. Now, again, if I increase the pressure, and I do that by decreasing the volume, Boyle's law, I reduce the volume, I compress the container in such a way that I were to increase the pressure, the system is going to say, let me decrease the pressure. Let me use my weird analogy I use in class. I were to take the entire class, we have like 25 kids in our classroom, okay? And I were to put you guys all into a very small space. Initially, it'd be like, this is uncomfortable. But it would get to a point where it's so uncomfortable, your first initial thought might be actually, can someone get out of here? Can someone just leave? Well, in this chemical reaction, as we see it, the irony is, going from left to right, we take 4 gas molecules and turn them into 2 gas molecules. So what that means is, this system, going from left to right, actually decreases in pressure. So when this shifts from left to right, the pressure decreases. So what happens is, if we decrease the volume, we increase the pressure, this system is going to shift towards the right. It's going to shift towards the side with fewer gas molecules. If we were to decrease the volume, get rid of all this pen stuff, so let me get rid of that because it's driving me crazy. If we were to decrease the volume, which means we increase the pressure, the system is going to respond in such a way that it tries to relieve that stress. It's going to shift towards the side with fewer gas molecules. Fewer gas molecules, not molecules in general, gas molecules. So if I were to squeeze this system, it's going to create more ammonia. In the Haber process, one of the things they do to try to increase the production is it's almost like a piston situation where it's squeezed and released. It's like it's squeezed to try to make more, and as it's being released, they then pump in more nitrogen and hydrogen, and then they squeeze it again. And then as it's expanding, pump in more nitrogen, pump in more hydrogen, squeeze it again. And every time you squeeze it, it shifts towards the right to try to make more of the product. The reverse is true, that if you were to increase the volume, it's going to decrease the pressure. So it's going to remove the ammonia. It's going to try to move towards the side that has more gas molecules and create more of the nitrogen and the hydrogen, which would be a bad thing for this process. Okay, so that's the end of LeChatelier's principle. Again, one of my more favorite concepts because it's very conceptual, a little bit of math involved. You'll see where the math is through the OWL problems where you'll see the changes take place. This week, we will be meeting on Wednesday and Thursday in teams. This is the last section, the last PowerPoint for Chapter 12. So come prepared on Wednesday and Thursday for questions. And we'll go ahead and chat about this chapter and such. Next week, we will start Chapter 13, which, just to make sure that we are crystal clear, the next chapter has 0 differences relative to equilibrium. We're still going to be talking about the same types of equilibrium. We're still going to be talking about ice charts. We're just going to be talking about a special type of equilibrium, and those are acid-base equilibrium. And we're going to focus a lot more on aqueous base. So KCs are going to play a bigger and bigger role in the next chapter. Hopefully everybody is staying safe and healthy and practicing your social distancing. Guys, I don't care what anybody says or anybody thinks at this point in the game. I'm very opinionated here. The virus is not dead. Stay safe. Stay safe. Stay safe. Practice your social distancing. Stay away from one another. I know it's hard. I know it's difficult, but I would love to have the opportunity in the very near future to have some degree of normalcy. And we're not going to be allowed to do that until we get all risks associated with this disease, this virus taken care of. So continue to stay home as much as possible. Don't think it's done just because the governor allowed you guys to leave the houses. Don't believe that it is dead and it's completely annihilated. Until there's a vaccine, until there's some type of a cure, it's still out there. And I don't want to have another influx happen so that next fall we spend the entire fall listening to my wonderful voice on YouTube videos. So anyway, take care, be happy, be healthy, be safe, practice social distancing, and I will see you on the next video. But before then, I will see you on Wednesday and Thursday this week. Always remember, never forget, you know this phrase that pays, sig figs really do matter. Toodles.